Welcome back, everyone. I hope you enjoyed exploring the outcrop through these digital methods. Datasets like these are being increasingly used by geoscientists in additional ways to capture and record data, allowing further study once they are back at their desks. In addition, it means that outcrops from across the world are becoming increasingly more accessible. We no longer have to get on long-haul flights to observe these really special outcrops. Now, hopefully you will have been able to identify that we have two main rock units present at Siccar Point. But not to worry if you didn't, as I will talk you through how we can identify them. There are a couple of ways in which we can identify these two rock units. And first of all, it's through the colour. The rocks towards the top left-hand side have quite a distinctive red coloration, while the rocks towards the base are grey. I have now popped on an interpretation of these two units, drawn a line where these two units meet to clearly separate them out. The second way we can distinguish between these two rock outcrops is through their orientation. The rocks at the base are near vertical, while the red rocks on top are gently dipping to the left-hand side of the image. If we schematically bring these together, we can see that the rocks have this relationship to one another, where they are at different angles. A key question from this observation is, how did the rocks get to have this relationship? We know that sediments from our last video are deposited on near flat surfaces, so how did Unit 1 become vertical? So I'm going to talk through a hypothetical situation here to try and help you understand how we get these flat sediments to become vertical. Now, the first thing we need to do is deposit that sediment. You can see from this example here, I have a river meeting the ocean. It's carrying that sediment out, which ultimately starts to slowly settle to the ocean floor. These sediments then form layers through time, but the ocean then starts to dry out. Now, but we still need to deform these flatline sediments to become vertical. If we compress these layers, you can see how we start to deform and fold these beds of sediment. Further compression leads to these folds to become much more defined, and you can actually see in areas in that 3D model that some of the beds are now near vertical. This compression ultimately forms topography, which rivers will then erode and transport sediment. Now, when Hutton observed these beds, he didn't fully understand the mechanisms by which they became vertical, and it wasn't actually until the 1960s and 70s that we have a real understanding of plate tectonics. But it shows how far ahead of his time he was. He understood that some large-scale process was deforming these once flat-lying rocks, but he didn't quite understand what that process was. Now, how do we form the second part of the outcrop, that red-coloured Unit 2? Well, as we mentioned previously, we form topography when we have tectonic plates colliding. This will then allow flow of water, often through rivers, and erode that landscape. So with further compression and tectonic forces, we can uplift those rocks, the rivers can become much larger, and then start eroding the landscape in which they flow over. Now, this can actually be observed when we look at this outcrop with Unit 2, as we can see Unit 2, with that dotted line I drew on previously, that it's eroding into Unit 1. And what this also allows us to confirm is the timing in which these events happened. Unit 1 had to be first of all deposited and then deformed for then Unit 2 to come over and erode into it. So now we have determined how Unit 1 became vertical and how Unit 2 then eroded into it. We want to understand how we interpret the environments in which the sediments were initially deposited in. Now, as geoscientists, what we do is study modern environments. Different environments around the world have distinctive features. So, for example, on the left-hand side of the image there, that is a river deposit. It's quite near the mountainous area, so the grains and the clasts are quite coarse. They haven't yet been broken down into small, fine sand particles. But it's a very distinctive deposit that we find in river environments. In desert environments, we see sand dunes. These sand dunes form nice little ripples on top. And for example, when we go to the beach, we can actually see beaches have very shallow dipping surfaces to the sea, and these can form horizontal laminae or very shallow dipping laminae, which we can see examples of just by the rock hammers handle there, but also we would also expect to see shells there as well. So we can use all of these observations that we have seen from the modern day environments and look for similar characteristics in the rock record. So for example, I've got a selection of images here from various sedimentary rocks on my travels and studies. And for example, in the bottom left-hand image there, we can see we've got these nice dipping faucets just coming down here like this. And through observation of modern processes, we actually know that these dipping faucets, which we call cross sets, form when underwater dunes migrate with the flow of the water. Another thing that can really help us deduce the sedimentary environment is fossils. So the top right image there is an example of a fossil that forms in the marine or deep ocean environment. So if we find that fossil, it can really help us understand what the sedimentary environment was. Equally, the bottom middle image, you can see some very subtle vertical lines going down that outcrop, and these are actually root traces. So we know that that material was deposited in a floodplain environment in which we then get trees or grasses growing on. But equally, we can see, for example, in glacial environments, we see certain types of deposits associated with them. Now, I would like you to return to the workbook and undertake exercise 2, where you'll try to determine the environment in which the sediments were deposited in based on the data given.